we can make an equation or two for relating force to the change in velocities and the time and its mass, just to make things easier next time if we need to do some calculations about the force. Now, so let's start. Let's start by turning this equation into a formula. So force would be F, and I need some way of writing down the rate of change of momentum in terms of the m, the mass m, initial velocity u, final velocity v, and the time. Right. So let me start from momentum. So change of momentum, I need to start from the initial momentum. Okay, so initial momentum is mass times the initial velocity. That's mu. Okay. The final momentum is mass times the final velocity, which is mv. Okay, so final initial momentum and change of momentum is the difference between the two. It's the final minus the initial momentum. And to find the rate of change, I need to divide the change of momentum by the time taken. Okay, that will give me amount of change, say per second, for example. And now I have the equation. I now have the rate. That's the rate, and according to the equation, force is equal to this rate. Remembering that this is for SI units only. So therefore, I have an equation. Okay, and we can actually simplify. We can simplify this equation in this way. Okay, write down F again. Now notice in this equation that I have m here and I have m there. This means that I can factor out the m. I can do this using algebra. I can say this is m, the bracket there. Okay, and if I take the two m's outside of a bracket, then what's left inside the bracket are v and u. So in the brackets I have v minus u over the time t. Okay, so we are almost there. Now then, if you look at this bracket, v minus u is actually the change in momentum. Now it's a change in velocity. Okay, and when we have change in velocity divided by time, that's acceleration. That's exactly what acceleration is. So that's really useful, because I can now say that I can now replace the v minus u over t, replace that by acceleration a. Okay, my a here, the a is acceleration. Okay. So now I have a really simple formula. F equals ma. Okay. So the numbers here looks all fairly straightforward. They can all come from what we have, say, in this example in the figure, where we have already numbers for v, t, and m, and u. Okay, so that's simple enough. Now, but there's something hidden in this equation, something a little more complicated that is hidden in this equation, and that is that if you remember, v here is actually a vector, u is actually a vector, okay, and force is also a vector. So what does this mean to the equations? Alright, so force is a vector and acceleration is also a vector. Okay, so the moment we have vectors, things can start to get complicated. Okay, now there are two cases that we should think about. One is about motion along a straight line. The other would be just motion in any direction. So we are going to look at some examples on these two types of situation. Okay, but first, before that, let me say a little bit more about a meaning that come from or something that these equations here would imply. Okay, so bear with me for a little bit more. I know that this is getting the equations are getting a bit abstract, maybe colorful. Okay, so right, if I for now, if I just look at the final equation, I'll just start with the final equation that I have, that force, I'm going to copy this out again, that force here, the force from there, is equal to ma, equal to mass times acceleration. Let me just look at this first. Now, if we remember that f is a vector and a is also a vector, then what does this equation mean about the vectors? What it means is this. A is a vector means that a, the acceleration, has a magnitude and a direction. Okay. When you multiply it by a number, m is just a number, no direction, not a vector, just a number. So when you multiply this vector a by a number, the answer must have the same direction as a. Okay. The effect of multiplying by the number m is to, if you like, change the magnitude of a, or if you like, change the length of a. Okay. So m just multiplies by the length of a, but the answer keeps the same direction. Okay, so that's our f. The answer is just the force f, right? So that means that f must have the same direction as the acceleration. Now this is a very important result. Okay, this is a very direct result of this equation. So we have to remember that this equation implies that f and a, force and acceleration, are in the same direction. Okay, we should remember that. Okay, and now let me go back a little bit to this equation here, this one. Now in this equation, I'm going to look at the connection between v minus u and the force, right? So the difference between these two vectors, the final velocity minus the initial velocity. Now we know what is, we think of this as the change in velocity. right? And it's also a vector. You have a vector v minus a vector u. We know how to find the difference between two vectors. We've learned about the triangle law and all that. So now notice that the acceleration a comes from the change in velocity divided by the time taken. So what this means is that this change in velocity, which is a vector, must also have the same direction as a. Okay, so change in direction has the same direction as a change in direction of velocity has the same direction as a. And that in turn means that the change in velocity must have the same direction as the force. So they're all connected. They're all connected together. And if we take this one more step backwards, we have here momentum, right? The final minus the initial momentum. And each momentum is a vector. So we have vector minus vector. And what we have here is the change in momentum. So the change in momentum, the difference between these vectors, change in momentum is also a vector. So this change in momentum vector, according to this equation, must therefore be in the same direction as the force. So from these few equations, we can read out a meaning, which is that the force is in the same direction as the change in momentum. Or if you want to think about cause and effect, right, we can think that change in momentum is the effect of the force. The force is the cause. So we can say that it might be better to say that the change in momentum is always in the same direction as the force. Okay. Now, if we look at the next equation, we could say that the change in velocity is always in the same direction as the force. And if we look at the third equation, we can say that the change, missing arrow here. The change, no, not the change this time. If I look at this equation, I can say that the acceleration is always in the same direction as the force.